Hello everyone, welcome back to another session of Heterogeneous Catalyst PYQ series. So here in this particular session, I'll be solving at least 10 questions, and at the end of the lecture, I think you'll be able to solve lots of previous year questions or again incoming questions that is coming in the gate in 2025, something like that. Okay, so let's begin with the question first here. The question says that in a solid catalyzed reaction, the diffusion effect are more likely to affect the overall rate of reaction, right? So here, the thing is that let's say if I'm assuming this one is a catalyst, a spherical catalyst, so the diffusion effect is more dominant. So when diffusion will dominate? So diffusion will dominate when larger pore size is there. So first I'll write the top, point wise that diffusion dominant diffusion dominating step. First one is a larger pore size, B is your a small particle size, and C is your slow reaction. So if reaction is low, then definitely diffusion is going to get dominated over there. So if these 3 points are being fulfilled in any kind of process in solid catalyzed reaction, then that will be a diffusion dominating process, right? So let's try to understand out of these options, 4 options, which one is correct. So fast reaction is fast reaction is not the case, so it will get cancelled out. Fast reaction, again second one will not work. Slow reaction, it can work. In catalyst for a small pore, this will not work, and slow reaction in catalyst of large pore diameter, so this will work, right? So I have written all of these 3 points. So if you remember these 3 points, then definitely for a strong pore diffusion and for a strong rate overall reaction conditions, you can identify your option, something like that. Okay, you can solve these things in this way. So this is just a theoretical question, but again from a heterogeneous catalysis system also, most of the time you'll see questions are coming from the theoretical basis, right? I'll be moving towards the next question, and the next question is, if a first order gaseous phase reaction is catalyzed by a non-porous solid, so there is a non-porous solid, let's say I'm assuming the kinetic reaction and the external mass transfer, the kinetic rate constant and the external mass transfer coefficient are K and Kg. So let's say if concentration of reactant in gas phase CAG, and when this is coming to the surface of the catalyst, concentration I am assuming is CAI. So here at the surface you will see that reaction rate constant is given as K and mass transfer coefficient is given as Kg. So you are supposed to calculate effective rate constant K effective in the given problem. So if I write the mass transfer, so definitely what is happening here, so here mass transfer is happening and again reaction is happening. Is that clear? So here concentration is CAG and again CAI, and here you can see this one is your reaction and this one is your mass transfer. So flux will be same, something like that. So that's why rate of mass transfer, here you can say rate of mass transfer, that will be equals to rate of reaction. So see, this one is the first order reaction. So you can say what is rate of mass transfer? Rate of mass transfer is convective mass transfer Kg into CAC minus CAI, and that will give you that small k into CAI. So from here we can calculate CAI. So you can write Kg into CAG, that is equals to, if I'll take common KCAI, so you can write Kg plus K. So from here you can calculate the value of CAI, that is the concentration at the surface. So CAI will be equals to Kg into CAG divided by Kg plus K. Right, now if I want to write the rate of reaction at the surface, that is equals to K into CAI. So you have calculated the value of CAI, you will substitute these things here. So rate of reaction, that is equals to K into Kg into CAG divided by Kg plus small k. So let's say minus of rate of reaction, that can be written as K into Kg divided by Kg plus K and CAG. So what is K effective? So this one will be your K effective. So the value of K effective from here you can calculate. K effective is equals to K into Kg divided by Kg plus K. So if you want to divide this thing something like that, so that can be written as like 1 upon Kg plus 1 upon K. So finally you can reorganize this thing. So 1 upon K effective can be written as 1 divided by Kg upon 1 upon K. This one will be your answer. Okay, so now you can go to your option and you can select which of the following options are correct. So from here your option D is your correct answer. Okay, so with that I'll be moving towards the next problem, and the next problem is from a pollutant P degrades according to the first order reaction. So let's say P is getting converted into some reactant product R having N is equals to first order reaction. An aqueous system containing P at 2 kilomole per meter cube. So Ca naught is given as 2 kilomole per meter cube. The volumetric flow rate, again volumetric flow rate is 1 meter cube per hour is given in a mixed flow reactor. So this pollutant is being entered into a mixed flow reactor, and the volume of reactor is given as capital V in meter cube. The concentration of reactant after coming from mixed flow reactor is bring down to Ca, that is equals to 0.5 kilomole per meter cube. The inlet concentration of pollutant is now double. So now this one is the first case. So finally Ca naught dash is double, so that is equals to 2 Ca naught, and the volumetric flow rate is triple. So volumetric flow rate V naught dash is equals to 3 into V naught, and the volumetric flow rate is triple. If the pollutant level is to bring down to the same level, so finally Ca dash is same, that is 0.5, the same level of 0. Then volume of the mixed flow reactor should be increased by a factor of. So you are supposed to calculate final volume V dash is what. So if I write V equals to V by V naught is equals to obviously Ca naught Xa divided by Kca naught into 1 minus Xa, or directly I will be writing Kca, because this is a first order reaction, right? Okay, and this one is my equation first, and second equation I can write V dash divided by V naught dash, that is equals to Ca naught dash Xa divided by Kca dash. But Xa you have to calculate, or let's say I'm not writing in terms of Xa something like that, so I'll be writing in terms of Ca naught minus Ca, and here Ca naught dash minus Ca, because final concentration is same. So now if I'll divide equation first and second, so I'll be getting V by V naught multiplied with V naught dash divided by V dash, that is equals to Ca naught is given to you. So how much? Ca naught is 2 minus 0.5 divided by K will get cancelled out. K multiplied with 0.5 multiplied with again K, and Ca dash is again equals to Ca, and that is equals to 0.5 divided by Ca naught dash. Ca naught dash is the 2 Ca naught, right? So 2 multiplied with 2 minus Ca is 0.5. So now from here you can cancel out this one and this one, and V naught dash is 3 V naught, right? So that will be equals to 3 multiplied with V divided by V dash, that is equals to 1.5 divided by 4 minus 0.5 is 3.5. So V divided by V dash, that will be equals to 1 by 3, that is equals to 1 by 7. So what is V dash? V dash will be equals to 7V. V dash is equals to 7V. Is that clear? So the volume of mixed flow reactor should be increased by a factor of. So final volume will be increased by a factor of 7. Is that clear? So your option A will be your correct answer here. Okay. Again, this one was I think the reactor design kind of problem from mixed flow reactor. But again, here what I'll suggest you to remember this formula. This is the design equation for the mixed flow reactor. If you know these things, then definitely you will be able to solve this kind of problem very easily. But only you have to get rid of the silly mistakes. That's it. Okay, so after that I'll be moving towards the next problem, and this problem is asked in 2005, which is a match the column kind of questions. So again, this question is very very important. So porous catalyst. So when we in which topic we talk about the porous catalyst. So I think for porous catalyst, Thiele modulus will be applicable. For parallel reaction B, selectivity is there. For non-ideal tubular reactor, dispersion number is there, that is 0. And for gas solid non catalytic system, so for gas solid non catalytic reaction, for D, I think Stigning core model will be valid. So your 3142 option A will be your correct answer here. Okay, this is very simple question. Now moving towards the next problem, this question is really good. So in this particular problem, you are supposed to calculate rate of reaction. So some data have been given to them, some data have been given to you from this particular problem. So you can see the rate at which an antiviral drug acts increases with its in concentration in the blood C according to the equation R. So rate of reaction is given like Kc divided by C50 plus C. This is a sigmoidal kind of reactions that is given, where C50 is the concentration at which the rate is 50% of the maximum rate, right? So C50 is the concentration where rate will becomes half of its initial value, means K by 2. So maximum rate is K here, right? And often the concentration C19 when the rate is 90% of the maximum is measured instead of C50. So the rate of the rate equation you have to calculate, right? So let's say this equation is given to you. So the rate will becomes 0.9 multiplied with maximum rate, which is K, when C is equals to your C90. Is that clear? So let's try to understand. I'll write K multiplied with 0.9, that is equals to K multiplied with C90 divided by C50 plus C90. Is that clear? That is the case here. So this K and K will get cancelled out. So finally you will left with 0.9 C50 plus 0.9 C90, that is equals to C90. So here I can write 0.9. This is just aptitude based type of question. 0.9 C50, 0.9 C50, that is equals to 0.1 C90. So you can calculate C50 is equals to 0.1 divided by 0.9 C90. So that is equals to C90 by 9. So C50 you have calculated in terms of C90. So now you can write the rate of reaction. Rate R is given as R is equals to Kc divided by C50 plus C. So but now you have calculated C50 in terms of C90. So you can write Kc divided by C90 by 9 plus C. So now you can see your option, which of the following options are correct. Option is correct. So I think from here your option B will be your correct answer. Okay, I hope everything is clear to all of you till now. Now I'll be moving towards the next problem, and this problem says that consider the following reaction between gas A and two solid spherical particle B and C. So you have two solid spherical particle B and C. This one is your B and this one is your C of the same size. So A plus B is getting converted into gaseous product having, so A will come, it will get react with B, A will come, it will react with B, and here rate of reaction is K1 and here rate of reaction is K2, and here it is producing gaseous product and here it is producing S. The S does not leave the particle C, so S is not going to leave the particle C. So if S will not leave, then what will happen? This S is going to get deposited on the surface of this particle C. So due to deposition of S on the surface of particle C, what will happen? The surface area which is available for the reaction or molecules of A, that will come and get binded to the another reactant C, it will decrease in terms of in second case, something like that. Let the S does not leave particle C. Let T1 and T2 be the time required for A to completely consume particle T. So here time is T1 and here it takes time T2. Is that clear? B and C respectively. If K1 and K2 are equal at all temperature and the gas phase mass transfer resistance is increasable, then what will happen? So here what is happening, I told you that here gaseous product is getting formed. So this gaseous product is not going to get deposited on the surface of this particle B, right? So every time A will come and it will, every time you will see free surface area is available for binding of A with B. So here you will see reaction will be very fast in terms of A. Why? Because surface area is always available. But in second case for C, since S is getting deposited on the surface of the particle, so if B has to completely convert it into gaseous product and C has to completely convert it into S, so B will get converted very easily or very soon compared to C. Why? Because there is no resistance due to S in case of B in comparison to the resistance occurred by the S in case of C. So what will happen? The time required T1 for complete conversion of B will be less compared to T2. So here you can see T1 will be less than T2. T1 will be less than T2 at all temperature. Sorry, T1 will be less than T2 at higher temperature, obviously, something like that. Is that clear? So what is the rate determining steps here? The deposition of S in case of C, which is not there in case of B, right? So this one was the crux point here in this kind of problem. Now I'll be moving towards the next problem. I hope this problem is clear to all of you. But again, this logical based questions can be asked, but you have to read the question first, and after that just don't see the question and don't run over the question. I'll suggest you read the question first, try to analyze what you have learned, and after that, if you have learned all of these theories, then definitely you will be able to solve the problem, right? But don't try to run over the question. Now the next question says, this is also a very important kind of question. So this is a statement for the linked answer kind of question. So consider the diffusion of a reactant A through a cylindrical catalyst pore. So let's say I am assuming there is a cylindrical catalyst pore, something like that, okay, having radius is R, capital R. This radius is capital R and length is L, where L is very greater than R. Reactant A undergoes a zeroth of the reaction, so minus of Ra, that is equals to only K, right? So if A is getting converted into any product, N is equals to 0, having rate constant is K. Cylindrical surface of the pore. The following equation describes change in the concentration of A within the pore due to the axial diffusion. So since reactant will come and start diffusing along this direction, and again reaction would be happening something like that. Diffusion and reaction will be happening in catalyst pore, something. So along this direction you can see at the surface of the pore reaction will happen, and along this direction diffusion is happening. So due to this reaction and diffusion phenomena, you can get a partial differential equation d2Ca divided by dx square, which is equals to K, where Ca is the concentration of A at a distance x from the pore entrance. So this one is the pore entrance. So here x is equals to 0 and this length x is equals to L. So if the concentration of A at the pore entrance is Ca naught, so if I do this, if you can see the boundary condition is here at x is equals to 0, concentration of Ca equals to Ca naught, that is given to you, okay, and at x is equals to L did and no reaction occurs, the concentration profile of A. So at x is equals to L, you will see del Ca by del x will be 0. Why? Because there is no flux boundary condition, because here nothing is going out, right? So that's why del Ca by del x will be equals to 0. So you are supposed to calculate the concentration profile along the length direction. So you can see this one is equation first. If I'll differentiate this equation first, so I can get dCa by dx, that is equals to kx plus c1. Again, if I'll differentiate this thing, so I'll get Ca, which is a function of x, that is equals to kx square by 2 plus c1x plus c2. So this one is the concentration profile, which is a quadratic concentration profile in terms of x, right? Now if I want to substitute the boundary condition, so first let's say at x is equals to L, del Ca by del x will be equals to 0. Is that clear? So I can say 0 is equals to k multiplied with L plus C1. So C1 we will be getting minus KL. Right, now at x is equals to 0, we have Ca equals to Ca naught, second boundary condition. This is just a ordinary differential equation kind of that thing. So I can write here Ca naught, that is equals to C2. Now I can write, we have got C1 and C2 both unknown constants, so I can write the concentration profile Ca at x, that is equals to kx square by 2 minus k L into x plus C2. This one is the concentration profile. So now you can match your option, which of the following options is correct. Kx square by 2 minus Kl into x plus Ca naught. C2 is Ca naught, so I'll substitute Ca naught here. So from here option A will be your correct option. Is that clear? So again, boundary condition can be changed, so anything can be changed, but here you have to understand that whether you are able to solve this differential equation or not with the given boundary condition. So there may be two different, obviously second order differential equation is there, so you will be having two boundary condition, but you have to understand how to substitute boundary condition to calculate the unknown, and from there you can calculate the concentration profile inside the porous catalyst. After that you are supposed to calculate the minimum pore length for A to completely converted within the pore. So if a reactant A is entering into this particular pore, right, having length is L, so if A has to completely converted, if I write, if A has to completely converted into product, the final concentration of A should be equals to 0. Is that clear? If final concentration of A will be equals to 0, or rate of reaction will be equals to 0 at that point of time. Is that clear? So in that case, what you can understand from here, so Ca will be equals to 0, then I can say kx square by 2 kx square by 2 minus kl into x plus Ca naught, that will be equals to 0. Is that clear? Kx square by 2 minus kl into x plus Ca naught will be equals to 0. Now you have to solve these equations. Is that clear? So I can write x square minus 2l into x plus 2 Ca naught divided by k, that is equals to 0. Okay, so once you will, this is just a quadratic equation, right? You can solve quadratic equation from here and you will get x value something. So the value of x that you are getting from here, that will be your answer. Is that clear? So you can solve this quadratic equation. This equation is not very difficult to solve. Okay, I hope this thing is clear to all of you. Now I'll be moving towards the next problem, and the problem says that a first order reactions to of A to R. So a reaction A is happening and it is getting converted into R, is run in an experimental mixed flow reactor. So you are having a mixed flow reactor. Find the role played by pore diffusion in the run given below. Ca naught is given to you. Ca naught is equals to 100 and weight is fixed. Agitation rate was found to have no effect on the conversion. So there is no effect of agitation, means external mass transfer has no effect on the rate of reaction, something like that. So only this phenomena is occurring due to the reaction and diffusion kind of thing, right? So what happens, you can see for a strong pore diffusion resistance region, if you see for a strong pore diffusion resistance region, rate is inversely proportional to particle size. Rate will be inversely proportional to particle size. So since this reaction is occurring as a first order reaction, so you can see particle size is increasing. So if I can say dp1 divided by dp2 will be equals to R2 divided by R1. If this things is happening, then we can say this is a strong pore diffusion resistance region or inversely proportional. So if diameter is increasing, then rate should be decreased. Is that clear? And what is rate? Rate is equals to K CA. Is that clear? Rate is equals to KCA. So can I write KCA naught into 1 minus XA? So rate is directly proportional to 1 minus XA. So you can say if XA is increasing, 1 minus XA is decreasing and rate is decreasing. So here you can see conversion is decreasing, so rate will be increasing. So if what is happening, if diameter of particle is increasing, rate is XA is decreasing, means rate will be increasing. So rate is increasing, right? Rate is increasing means this particular problem says that this is not going to happen in a strong pore diffusion resistance region, means diffusion does not have any effect, right, in this particular kind of problem. That's why diffusion free system will be there. Is that clear? If a strong pore diffusion resistance is region is there, then this particular thing should be valid, but exactly opposite phenomena is happening here. That's why that this particular problem will, or this particular thing should be happening in case of diffusion free region, something like that. Okay, so after that I'll be moving to the next problem. The problem says that a packed bed reactor converts A to R. So the reaction is happening, A is getting converted into R, having first order reaction in a 9 millimeter pallet order. The particle size is 9 millimeter in a strong pore diffusion resistance region to 63.2% level. So conversion here is XA is 0.632. If 18 millimeter pallet are used, what is the conversion? So what you can see, since this is a strong pore diffusion resistance region, so I can say dP1 divided by dP2, that is equals to R2 divided by R1, because R is inversely proportional to particle diameter for a strong pore diffusion resistance region. Is that clear? So diameter of particle is 9. At the end it is going to increase to 18, and R2, this is first order reaction, so K Ca naught into 1 minus, I can write Xa2 divided by K Ca naught into 1 minus Xa1. Is that clear? So here you can see K is not going to change, K will get cancelled out, Ca naught K. So 1 by 2, that is equals to 1 minus Xa2 divided by 1 minus 0.69, sorry 632. Is that clear? So finally you can calculate 1 minus 0.632. So that will be equals to 7.8 plus 30. So 37.8, right? So 0.378. So 0.378 divided by 2, that is equals to 1 minus Xa2. So the value of Xa2 will be equals to 1 minus 0.378 divided by 2, that is equals to 1 minus 0.189. Is that clear? So 189. So that is equals to 0.11. So final conversion Xa2 will be equals to 0.11. So you can see that if you are increasing the pore diameter, so sorry, something is there. 1 minus 0.378 divided by 2. So if a strong pore diffusion regime to 63.2%, so 0.632. So 0.1. Okay, so that is 0.37189, 0.189 plus 0.1 minus 0.189. Okay, so you can check the calculation, but the process will be same. The calculation mistakes may be there. You can go and make it correct, because this is a strong pore diffusion resistance region. So obviously rate of reaction will be inversely proportional to the diameter of particle. Is that clear? Oh, sorry, this one is happening in packed bed reactor. Sorry, you cannot use this concept, right? Let's try to understand one more time. Actually, this one is happening in packed bed reactor. I just okay. So for this kind of problem, what you can say, that you can write now, for equation you have to write here is W by Fa naught, that is the packed bed reactor, that is equals to 0 to Xa dxa divided by minus Ra. So this one is the first order reaction. And what is eta epsilon? Eta is R observed divided by actual rate of reaction. Is that clear? So we get to know. So here you have to substitute R observed. Okay, so from here what you can say, R observed, that is equals to eta multiplied with minus actual rate of reaction. So this one is your actual. Now you will be substituting this value over here. So what I can say, that W divided by Fa naught, that is equals to 0 to Xa dxa divided by eta multiplied with minus Ra actual now, right? So I can write W multiplied with eta divided by Fa naught, that is equals to 0 to Xa dxa divided by minus of Ra actual now. Is that clear? Okay, so now what we can say, W multiplied with eta divided by Fa naught, that is equals to, I can write directly these things, 1 upon k ln 1 minus Xa and kCa naught. Is that clear? These things, since this is a first order reaction, so directly I can get W, and weight is given also, no. Okay, so let's try to understand. W into eta into kCa naught divided by Fa naught, that is equals to ln 1 minus Xa. So this value will be minus ln 1 minus X. So for a strong pore diffusion resistance region, for a strong pore diffusion resistance region, what you can say, effectiveness factor eta 1 divided by eta 2, that will be equals to phi 2 divided by phi 1, which is equals to R2 by R1. Is that clear? Phi 2 by phi 1 divided by R2 by R1. Okay, so from here we can write that eta 1 divided by eta 2, that is equals to minus ln 1 minus x1 divided by minus ln 1 minus x2. Is that clear? Because effectiveness factor here, eta is directly proportional to minus ln 1 minus x1. Okay, so now we can say that eta 1 by eta 2 is directly proportional to R2 by R1. So in place of eta 1 by eta 2, I can write R2 divided by R1, that is equals to ln 1 minus x1 divided by ln 1 minus x2. So R2 that is the diameter or d2 by d1. So now you can substitute that 18 by 9 directly. 18 by 9, that is equals to ln 1 minus 0.69 632 divided by ln 1 minus x2. So from here you will be getting the value of x2 will be equals to 0.39. Is that clear? So this one is very important kind of questions where you have to use this formula. So here I have seen later that there is a packed bed reactor. So for the packed bed reactor you have to solve this kind of problem in this way. So and this particular things are valid only for the strong pore diffusion resistance region. So whenever we see this kind of concept, this is only valid for a strong pore diffusion resistance region. So this concept you should remember. Okay, I hope this question is clear to all of you. Now I'll be moving towards the next problem, and this question says the following rate concentration data are calculated from experiments. Find the activation energy temperature for the first order reaction. Okay, so here dpca minus ra and temperature is given to you. So you are supposed to calculate the activation energy. Okay, hello. Okay, so here you can see the concentration, rate and temperature data is given to you, and again if diameter of particle is increasing from 1 to 2, the rate of reaction is also increasing. So this is not lying in a strong pore diffusion resistance region. And again when the particle diameter is constant, rate is also increasing, right? So here you cannot say there is a strong pore diffusion resistance region or weak pore diffusion resistance region, but directly you can have a formula of that rate of reaction that is equals to kCa. So I can write rate of reaction that is equals to k naught into e to the power minus e by RT into Ca. Is that clear? So rate is also given, concentration is also given, and temperature is getting varied, and you have to calculate the activation energy. So if I want to write R1, that is equals to pre-exponential factor is not going to change, e to the power minus e divided by RT1 into Ca1, and again if I want to write R2 can be written as k naught into e to the power minus e by RT2 into Ca2. So if I am assuming this one is my equation first and this one is my equation second, so if I divide equation first and second, so I can get R1 divided by R2, that is equals to e to the power minus e by r, and I can say 1 upon T1 minus 1 upon T2, and again Ca1 divided by Ca2. That's it. This is a very simple question. This is like RNS equation kind of problem. So R1 and R2 is given to you 1 upon 2, and that is equals to e to the power minus e by 8.314 into 1 upon 480. Okay, so here you have to use these things because temperature is also varying, concentration is also varying, right? So I will be taking R3, that is K3 and Ca3, something like that. So this is T3 and Ca3. So 1 upon 480 minus 1 upon 500 multiplied with Ca1. Ca1 is how much? 20, and Ca3 is your 40. Is that clear? So from here what you can calculate, the activation energy is this one. So it will get 2 and 2 will get cancelled out. So you can write 1 is equals to e to the power minus e upon 8.314 into 1 upon 480 minus 1 upon 500. So after solving these things, you will be getting the value of, let's say, E by R. So that will be equals to 4865.68. Okay, so from here your option B will be your correct answer. Okay, so with that I'll end this lecture here only. In the next lecture I'll be starting with another problem, and in one more lecture is required to complete all the previous year questions for your heterogeneous catalytic reaction. So what I'll suggest you try to keep searching for this video, and whenever I am putting the video, just go through all of these videos. So in only 1 or 2 lecture you will be able to complete, learn all of these concepts from the heterogeneous catalytic reaction system, as well as lots of question I am doing from the previous year also. Okay, thank you all for attending the lecture. See you in the next class.